Hey there, it's Shannon Math Chick Myers, and today we'll be taking a look at the very first section of the workbook that I wrote for elementary linear algebra, and that is called Linear Systems and Matrices. Let's check it out. Go ahead and warm it up a little by solving these systems of linear equations, and there's just two items there. And do them, however you're used to doing them, but please do them by hand. And then, so go ahead, pause the movie, and then you can go along with me to see how it's going after you complete them. I will be working these a little bit differently in order to prepare you for how you would solve something like this by hand using matrices. Okay, so pause the movie, warm it on up, and I'll check back with you in a minute. Alrighty, let's see how you did. For this first part, I'm going to go ahead and name our rows. Let's call this one row 1, the very first equation, and the second equation in the system, row 2. So first off, if you remember, as long as you do the same thing to both sides of one of the equations, the same operation that, allowed operations, then you haven't changed the equation, just how it looks. And so similarly with a system of equations, as long as you follow the, equality rules for each individual equation, you haven't changed the system. And even if you add equations and stuff like that, you haven't changed the system, just how it looks. And that's how we, solve these complicated looking problems by hand and using the computer. So let's check it out. First off, this system set up where it'd be pretty cool just to use substitution, since the second row here just is a linear equation in one variable. So I'm going to go ahead and do this. I'm going to say, all right, we've started out with this one system. I am going to alter the system by multiplying row 2 by 1/6. And this is going to give us a new row 2 for our system. So our new system is going to look like this. We will have the first equation stays exactly the same. And the second equation becomes what? Beautiful. X is equal to 2. Good so far? All right. So now it looks the same, it being the system, but you have a new row 2. So coming back up here, let's see what we're going to do next. Well, we know that x is equal to 2, right? So now we can just, what? Substitute x equals 2 into row 1, and that will enable us to solve for y. Alrighty, so let's do it. Row 1, instead of putting negative x, we'll put negative 2, because x was equal to 2, plus 8y is equal to 3. So here, n for x, oops, sorry about that. N for x, we're putting in this 2, right? So we now have negative 2. When I move it to the other side, I add 2. So we're going to get 8y is equal to 5. And then what? Beautiful. Dividing both sides by 8, y is equal to 5/8. So what do we get for at the end of the day, what have we gotten? What does this mean? Well, it means that if you think about this as a conclusion, if you will, our goal here was to just solve this system. Well, we got a system which is considered consistent because we got a solution. So if you get a single solution or infinitely many solutions, your system is consistent. This is important. So we got a single ordered pair solution, which means what? These two lines, beautiful, intersect at exactly one point, and that point happens to be 2, 5/8, and it's the set containing that point. And this system is consistent. And it turns out that it has independent equations you get independent equations if you are not collinear, you being the line. So if the two lines are not collinear, or if there is no part of your system, in this case it was a system that's an R2, but we're going to be going, we're looking at Rn very soon. So if any portion of your system is whatever, collinear, coplanar, etc., then you end up having a dependent equation situation. All right? So just ponder that. Now, I know that you may be sort of thinking, oh my gosh, why are we doing this? I'm in linear algebra. I'm way more advanced than this. The reason for this is that your goal in this quote unquote easier part is to learn it super well, way better than you ever did. You don't want to just be able to solve the equation. You want to be able, or the system, you want to be able to know what's going on kind of behind the scenes. All right, so let's take a look at this one. Do you see part B is also set up for substitution? And in fact, when we were altering this system in part A, we actually got this into reduced echelon form. So we will be learning specific definitions for these things soon. But basically what this means is that reduced echelon form means that you have the system ready to back substitute. Okay? So, do you see in part B, you're all ready to back substitute because it looks like this sort of upside down triangle, right? If you sort of look at this right here, you see how it's kind of an upside down triangle? So, let's just go directly into back substitution. So first, we will substitute z equals 1 into, again, if we have row 1, row 2, and row 3, we'll be able to solve for y. Alrighty, so putting that into practice, we'll have 2y plus 4 times good, 1, is equal to 0. So then we'll get 2y is equal to negative 4, and y will equal negative 2. So all I did was I had my z was equal to 1, so I plugged it in here and here. Now, the next step will be going into row 1 and back substituting what we got for y and z so we can solve for x. So let's do it. I guess I can number these. So 2, substitute, z equals 1 and y equals -2 into row 1, and that will enable us to solve for x. So 3x plus y, so n for y, we'll put -2, and then minus z, so z was +1, and that's going to equal to 15. Alrighty, so here was our z. We got the value for y on this step over here, our last step, and then we'll have what? 3x minus 3 is 15, and so then 3x will be equal to, adding 3 we'll have 18, and then x will be equal to 6. Good so far? So, all right, our third step for this one, we want to have our, again, some kind of our conclusion going on. So what does it mean? We got what for our answer? Beautiful, a single ordered triple, right? So these 3 planes, now these are planes because we're in 3 dimensions, intersect in exactly one ordered triple. So put it in our set. X was 6, y was -2, and z was 1. So we have a set of one ordered triple. And then this system had a solution, right? We didn't get a contradiction anywhere. So this is a consistent system with awesome independent equations. All right, are we all warmed up? Very good. Let's go ahead and box these final results. A lot of times, just so you know, I don't have you ever, we don't always have these little math warm-ups, but when we do, it's because I have some sort of an evil plan that coincides with what we're doing. So just be patient and go along with the plan, and we should all be good. We're going to take a look at some definitions, or two definitions. So the first one is a definition of a linear equation in n variables, right? You have likely been used to dealing with x, y, z, w, right? Well, we could have, n equals 100, meaning we could have 100 different variables. So in linear algebra, what we start doing is using subscripts. Instead of just x, we'll often use x1, and then in place of y, we'll use x2, and then in place of z, x3, etc., all the way until we get to xn, whatever dimension of R we're in, all right? And this one has the form, well, you have coefficients. So you have the coefficient for x1 we'll call a1. The coefficient for x2 we'll call a2. Coefficient for x3 we'll call a3. I think you're seeing the point here. And this would go all the way to an times x sub n. And then that's going to equal to some constant b. All right? So here in our system that we just solved, right, our very first equation, row 1 right here, we had a linear equation in 3 variables, right? X, Y, and Z. So if I rewrote this in the other terminology, my A1 would have been 3, my x1 would have been x, my a2 would have been 1, x2 would have been y, a3 would have been -1, and then x3, or z would have been x3, and then 15 would have been our b. So let me write that in, all right, just so we can check it out. So from row 1 of warm-up B, we had 3x minus y, right? Plus y minus z was equal to 15. So from that one, A1 is 3, x1 is x, A2 is +1, x2 is y, A3 was what, -1, right? And then x3 was z, and then our b was 15. So you can see that, this is a note, you can see that systems are going to be made up of several of these linear equations. Cool, cool? All right, so then let's continue. The coefficients A1, A2, A3, all the way down to AN are real numbers. We're dealing with real numbers in this course. This is an elementary linear algebra course, so we deal with real numbers. And the constant term, B, is also a real number. The number A1 is called the leading coefficient. And x1 is the leading variable. Linear equations have no products or roots of variables, and no variables involved in transcendental functions. Transcendental functions are like logs, exponentials, inverse trig. So, give an example of a linear equation in 3 variables. Well, what do you think? Go ahead, pause the movie, come up with one, and then check it out. All right, so the one I'm going to come up with is x1 over 2 plus 5x2 minus root 2 x3 is equal to 5. I purposely did this one strangely so that you could scope it out and find the difference between, roots of the coefficient versus the roots of the variable. So here, and the other tricky things. So let's just identify my A1 is what? Awesome, 1/2. My A2 is +5. And then my A3 is -√2. Notice these are all real numbers. Definition of solutions and solution sets. And you really need to, again, pay attention to this stuff and learn it really well. A solution of a linear equation in n variables is a sequence of n real numbers. So S stands for solution set, or solution, and then they'd be in a set. So S1, S2, S3, all the way down to Sn, and it's a lowercase s. And they're arranged to satisfy the equation when you substitute the values. x1 equal to S1, x2 equal to S2, x3 equal to S3, all the way down to xn equal to Sn. Cool so far? So when you substitute or replace x1 with s1, x2 with s2, blah, 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 etc., all the way down to xn equal to Sn, into the equation, you should get an identity statement, right? So the set of all solutions of a linear equation is called its solution set. And when you've found the set, you have satisfied the equation. To describe the entire solution set of a linear equation, we want to use a parametric representation. Parametric representation is something we will use all throughout this course, so you want to make sure that you have it down right away, okay? So, general rule of thumb, right, is that you have to have at least as many equations as you have unknown variables in order to be able to solve a system of equations, all right? So I know right away that this linear equation in example 2 is dependent because it has two unknowns, x1 and x2, and it only has one equation. So it's not a system, it's just a single linear equation in two variables. So the convention is to isolate the first variable and write it in terms of the others, all right? There's going to be more than one solution to these things. I can't show you every single way on the videos, so I will typically be isolating that first variable that's in the linear equation in terms of the other variables. So in this case, we would basically just have what? Well, if I isolate x1, I will get 10 minus x2. Good so far? All right. So if I now let x2 equal to t, so another convention is if you only have one parameter, we often name it t, or I often name it t. If we have two parameters, they're often named s and t. Three parameters are s and t, etc. So that's how I will name them. And so if I let x2 equal t, what will happen? Well, I'll have x1 is equal to 10 minus t, and then I'll just rewrite here that x2 is equal to t. So this system here is consistent because it not only has one ordered pair, which will satisfy the equation, it has infinitely many ordered pairs that will satisfy the equation. So it's very consistent. But it does not have independent equations. So for this reason, we need to put a little bit more work in describing what's going on, okay? This is the basics for set builder notation, which is what you will need to use. And you will need to do it in this manner. So here we go. We got a solution set, right? Now, just like before, we're putting an ordered pair. But remember that this ordered pair is a little bit more complicated, right? Because there's an unknown in there. So we need to describe it, all right? And put any limitations on there that we find to explain. So this very first part, well, let me write the whole thing. Okay, so the colon, or if you do a straight line, means such that. And then we need to describe what number set t belongs to, or if t has any other limitations, right? Well, t must be a real number because that is what we are working with. Good so far? All right, so let's kind of dissect what's going on. So in this very first part here, we describe the form of the solution. So there's two things going on here. We're showing one that it's an ordered pair solution, and the other thing we're showing is that we've got this relationship between the first variable and second variable. The first variable is 10 minus that second variable. That's the relationship they're sharing. Okay? Now, this part here, the colon, or remember a straight line works, translates to such that. So this is where the description of the parameter comes in. And now we also have another nifty little shortcut. So this epsilon means is an element of. I'll often say belongs to, is part of, something like that. Cool, cool. And then the R, of course, stands for the set of real numbers. Cool, cool. So at the end of the day, just to kind of clean it up a little bit, we have just one equation we're solving, and the solution to this equation is the set of ordered pairs 10 minus t, comma t, such that t belongs to the real numbers. And it's not a system, so we don't need to talk about whether it's consistent or not. All right? Okay, so next up, solve the linear equation. So again, why don't you pause the movie, see how you do, and then check out how I'm working it, and we'll go from there. All right, let's see how you did. So again, I'm going to isolate the first variable, okay? If you wanted to isolate x2 or x3, that's fine. I'm going to isolate x1. So, x1 is equal to, well, I'll say 2x1 is equal to positive x2, right? And then minus 5x3, and then we still have that minus 1 hanging out. Good so far? So, x1 is equal to 1/2 x2 minus 5/2 x3 minus 1/2. Or you could factor out that 1/2 and write it that other way. Okay, so now we need to figure out how we're going to parameterize it, okay? So if we have x2 equal to s, and if we let x3 equal to t, what's going to happen? x1 will be equal to 1/2 s minus 5/2 t minus 1/2. And then I'll just rewrite them. x2 we called s, and x3 we called t. So how would we write our solution? Good, we'd have an ordered triple this time. The first one is 1/2 s minus 5/2 t minus 1/2. The second one is s, and the third one is t, such that s and t belong to the real numbers. And we're done. Cool, cool. How'd you do? Awesome. I knew you could do it. All right, so now we build on the definition from before. Now instead of just a linear equation and n variables, we talk about a systems of linear equations and n variables. A system of linear equations and n variables is a set of m equations, each of which is linear in the same n variables, right? So here we've got, and this is very general, all right? This is so that if m doesn't equal n, you're good, all right? So here, basically, what you're going to have is you're going to have m rows, okay, where each row is an equation, and n columns, where each column represents a specific variable, x1, x2, x3, etc. Cool, cool? All right. So solutions of systems of linear equations. A solution of a system of linear equations is a sequence of numbers, s1, s2, s3, down to sn, that is a solution of each of the linear equations that are in the system. So the solutions that you get have to work for every equation in the system. Cool, cool? All right, so now let's just check out the looks of some of these things and remind ourselves a little bit about earlier algebra explorations. So what I've done here is I have set up these systems that look quite similar, okay? Quite similar. Oh, my bad, there's a typo here. This last one should have been 24. Okay, so please change that in your guided notes. But go ahead, pause the movie, work these out any way you want. You're going to work them out algebraically on the left, and you're going to graph them and solve them graphically on the right. So if we should be able to use a scale where it's 10 by 10. All right, so go ahead, pause the movie, do your thing, and then play it again to see how you did. Okay, so let's see how we did here. So on these here, if we graph them first, all right, so I've got these two equations for part A. So remember, for graphing, there's different ways for graphing. You can pick two ordered pairs, you can find the zeros, whatever it is you want to do. I'll go ahead and just find the zeros. So if x is equal to 0, then y is going to be -8. Are we okay with that one? So I'll do, for the first one, I'll do it in pink. So I have a point at 0, -8. And if y is 0, x is going to be +8. So I'll have an ordered pair at 8, 0. And then it's just a matter of drawing your line and connecting those dots. Cool, cool. So this one is our x minus y is equal to 8. Cool, cool. All right, so I'll do the next equation in blue. So again, if x is 0, on the second equation that I underline in blue, y is going to be 2. So 0, 2. And then if y is 0, x will be 2. So I'll have those two ordered pairs. And what happens? They meet exactly at one ordered pair, and this ordered pair that they meet at is what? Beautiful. The ordered pair, +5, -3. Cool, cool. So that is how you'd solve it by graphing. Now, what if you wanted to, solve this using some other method, right? Well, do you remember you can add equations, right? So if we go here and we solve it algebraically, we started out with x minus y equals 8, x plus y was equal to 2. And we have opposing signs already on the y's. So we can use elimination and we'd get 2x plus 0y's, which is 0, would equal to 10. And that would give us x is equal to 5. And then back substituting, right, into one of the equations, I can do the first one, x minus, 5 minus y equals 8. Negative y would equal to 3. So y would equal to -3. Cool, cool? All right. So 5 is what I had gotten for x, and so I substituted it in here after using elimination or addition. So it's called different things in different textbooks. Cool, cool? So I've solved it algebraically as well. So at the end of the day, right, in our grown-up math notation, we got the set of a single ordered pair, 5, -3. This is a consistent, beautiful system. With independent equations. Okay. So now let's see how the next two went. Notice that the first equation is exactly the same. So I'll do it in the same color real quickly. so we don't waste time. And then we'll have the next one. All that changed was the sign in the middle. So this one we'll do in, I guess, purple. So if x is 0, y will be -2. And if y is 0, x will be +2. And so we will get something like this. And lo and behold, look at that. They look pretty parallel. Okay, well, do these lines intersect? No, right? So here, these are parallel lines, right? So that's what the picture looks like, right? Parallel lines, they don't intersect, and so therefore there's no solution, right? So here, no intersection, so no solution. But we don't just say no solution, okay? What we need to say is, we need to say that there is no ordered pair where these two lines intersect. So that's the empty set brackets, or you can represent the null set with the 0 with a line through it, okay? And this system is an inconsistent system. With independent equations. The most important part to remember is whether they're consistent or inconsistent for later. And so that's the solution for this one. And then just to take a look at this one, part B, algebraically, you'd have your x minus y is 8, x minus y is 2. So this is equivalent to the system -x plus y is -8 if I multiply the first equation by -1. The second equation will remain the same. And if you add them, what happens is you get 0 plus 0, if you will, is 0. 0x is 0 plus 0y, which is 0, so you get 0, is equal to -6, which is a contradiction. And that tells you, if you're solving something algebraically, that you have a no solution situation. All right? All right, so then part C, right? If we take a look at this, and a lot of times the way to do this would be to rewrite each equation. Notice that if we divide the first row, right, the first equation by 2, we get x minus y is equal to 8. If we divide the second equation by 3, we get x minus y is equal to 8, right? So the situation is it will overlap, right? So your picture would, look something like you'd have something like this. And then you'd, have this other line overlapping it. Right? So that could be this one here. Cool, cool? All right. So this gives us a visual of what we're working with. Now, how would I represent that? How would I represent this one? I mean, both of them are x minus y equals 8, right? So what should I do? Perfect. We want to parameterize, right? So we got something that's collinear, dependent. So we need to parameterize. Cool, cool. So what did we have? We had x minus y is 8. If we let y equal to t, we would have x equals t plus 8. All I did is isolate the x, right? And then y is equal to t. So then in our set builder notation, what would we have? We would have the ordered pair t plus 8 comma t such that t belongs to the real numbers. This is a consistent system. There's infinitely many intersection points. And it's got dependent equations. Now, as you get further, like to planar, where you're graphing planes instead of lines, it wouldn't mean that all of the linear equations were dependent. It could just be two of them were, right? So, but in this case, there's only two equations, so we can definitely write it like that. Awesome. All right. So, number of solutions of a system of equations. For a system of linear equations, precisely one of the following is true. This system could have exactly one solution, like the first example. This system would be consistent. The system has infinitely many solutions. That's like the last part C that we did. And this is a consistent system because it has infinitely many points of intersection. This system could have no solution. And this type has the parallel lines, planes that never all intersect at one plane or one line of the plane or whatever, one point in the plane, at least one point in the plane. So that would be an inconsistent system. So I can show you what that looks like. I mean, we just did what that looks like in R2, right, which is 2 dimensions. So this first one has exactly one solution. And remember, we said it was consistent. The last one has infinitely many solutions. And remember, we said that was consistent. And the second one, no solution, no points of intersection. Okay, so you've gotten a visual of R2 for the different types of systems. Now, so what did we learn from the last example? What is a picture? What does a picture look like? The only picture for an inconsistent system is parallel lines, right? And then consistent systems, you could have one intersection point or lines which are collinear. They're the same line, right? And so that's infinitely many points of intersection. If you've got three equations, three variables, there's different ways of being inconsistent. You could have parallel planes. So let's see if it works for us. Fingers crossed. Here is a wonderful resource called Calc Plot 3D. You can just search for that. So here, these are what my links were supposed to go to, but that's okay. The easiest way to have three different planes is going to be for us to have this same signs on the variables, right? Different constants that they're equal to. So we want to add to our graph an implicit surface, right? We don't want to isolate one of them. Just to make it easy, I could have the first thing be equal to -2, right? And I don't want to power on any of these variables, right? So if I have x plus y plus z is -2 for the first one, and then I'll have them all arranged between -2 and 2 is fine, actually. You see how we have that equation, all right? And then we want to add to the graph another implicit surface, okay? It's got our same graph, or it doesn't have our same graph, it has a new one. That's okay. Let's delete it. I copied the other one, so we can paste it. And then here, let's have this one equal to 0. Notice it's the same color, which is harder to see, right? Let's go to the settings on this one, and let's do a constant color. We can make this color blue or something, I don't know, light blue. And then for this one, so we've done that guy for this equation. Let's have this be a little more cheerful of a color. Put this one as yellow. And then let's add another implicit surface. And when we do this one again, I want to take all that out. Paste, and then on this one I'm going to say it's equal to 2. I'm going to put this in. We want to have a constant color other than gray. I don't know why that's the default. It's so ugly. All right, so do you see here, you can see at this angle, this is a nice angle here, we've got three planes that don't intersect at all with each other. Cool? Is an example of inconsistent in R3. Parallel planes this one. So intersecting two at a time. And we'll change it up. So intersecting two at a time, one of them will be where, one easy situation is where you have two of the equations that are multiples of each other. So if I made this top one, if I multiply it by 2, and then -4. Okay, so do you see that the equation that I'm working on right now is the third equation down multiplied by 2? So let's see what that looks like. All right, so here we go. That's what this guy would look like. So here's one where we're intersecting planes are intersecting two at a time. And another way that planes can connect two at a time is where you've got one plane that kind of cuts through the other two planes. I don't know, X, I'll do a minus here. And you did change this back to the first, like we had it at first. And then you can just toggle your view, however you want. But this is the big picture idea, no pun intended. So you can see what's going on. So notice that there are intersections, right? But they don't all three intersect in at least one point. Okay. So here's the other situation for that. Now, let's also take a look at different ways three planes to be dependent. Okay, so you can have linear intersection or planar intersection. So let's do the planar intersection now. Here, I think the best way if you basically would make it where they're all multiples of each other. So if I have x plus y plus z is 2, if I have negative x minus y minus z equals -2. I think that should do it. And let's do, I'm going to kind of extend the window on it. Maybe then we'll get to see how they look different. So you can see how they're coplanar there, right? And then now I need to have this one be a multiple. So if I double this one, or double the first one rather, and it would have to be equal to, what, 4? And then if I have this one go from -4 to 4, -4 to 4 on each of them, oh, this one, sorry, needs to be -2. There we go. So now, isn't that kind of a cool picture? You can see with rotating it around and stuff, you can see they're all coplanar. All right? Okay. So here's the planar intersection, and then the linear intersection. We have what I'm going to do here to make, I'm going to have 2 of them be coplanar, and then make sure that the other plane intersects these guys. So what will happen is we would have, I'll keep the first 2 the same, and then the last one I'll just have be some other kind of random plane. So I'll have this just be 2, actually, I'll have it be x minus y minus z equals 2. See what that gives us. There we go. Very good. And then we don't need it to be that big. Here we go. So do you see how it intersects these other 2? And just so that we can see, I'll have, what was this one set at? I'll have this one go to 3 as well, I guess. Three, and 3. Let's see what happens if I do 3.5. What I'm trying to do is give you, a sense of that. There we go. Perfect. Wanted to give you a sense of that planar intersection, how it's the same plane and you've got this other one cutting through it. So basically they all 3 intersect at the same line, but 2 of them are coplanar. Cool, cool? All right. Sorry about the dysfunctional links. So this equation here is an example of 3 planes that intersect in exactly 1 ordered triple. So I don't know if you can see it very well here, but right here, this is actually the ordered triple 3, -1, 1. Okay, and that's what that would look like, where you'd have just a single ordered triple result. Okay, so next up we have operations that produce equivalent systems. So we've already practiced some of these, but let's just go ahead and, get them all on paper so that we're all on the, kind of same page in case it's been a while since you've done these. Each of the following operations on a system of linear equations produces an equivalent system. And this is what I was trying to stress when we were doing those warm-up problems. So you can add 2 equations. You can multiply an equation by a non-zero constant. And you can add a multiple of an equation to another equation, even if that other equation is a multiple of its original self. All right? The evil plan is to get the system into what I was talking about, row echelon form. So if you hear anybody talk about REF form, that's what they're talking about. And remember that whole kind of upside down triangle we were looking at before. That's the how you want to get your left side of your equation looking, the one that has the variables. All right. All right. So now let's go ahead and define a matrix. So if m and n are positive integers, and m by n matrix, read m by n matrix, is a rectangular array, and it looks something like this. So you have, going across, you have A11, A12, all the way down to A1n. And then the second row, A21, A22, all the way down to A2n. Each column goes A11, A21, all the way down to AM1. So you have M rows and N columns. So matrices are so powerful. I don't know if you've ever used MATLAB. The free version, or a free version, is Octave. It's amazing. And it, you have to know how to use matrices for the coding of them. And this is at this point in time in 2019, I've heard this is a very desired ability in order for you to get internships and jobs. So it's all very good. I'll show you a little bit of how to use Octave soon, maybe even today. All right, so here you've got this matrix A, right, in which each entry, Aij, of the matrix is a number. And M by N matrix has M rows and N columns. Matrices are usually denoted by capital letters. Okay. Now, the entry Aij is located in the ith row and the jth column. The index I is called the row index. Why do you think so? Because it identifies the row in which the entry lies. And the index j is called the beautiful column index, because it identifies the column in which the entry lies. A matrix with m rows and n columns is said to be of size m by n. When m equals n, the matrix is called square of order n, and the entries A11, A22, A33, all the way down to ANN are called the main diagonal entries. Okay, 3 important types of matrices. We have diagonal matrices. Diagonal matrices are square matrices with ones along the main diagonal and zeros elsewhere. Makes them very easy to compute with. The main diagonal goes from the top left corner to the bottom right corner. Coefficient matrices are formed using the coefficients of the variables. in systems of linear equations. So we use coefficient matrices for a lot of things, one of which is finding out whether a set of vectors spans, right, is one really important application, and many, many others. All right, and then we have augmented matrices. And they adjoin the coefficient matrix with the column matrix of constants. All right, so here we go. Example 5. Consider this system of linear equations, all right? I won't read it out to you, but it's well, I guess I can. x1 minus x2 plus x3 is 2. Negative x1 plus 3x2 minus 2x3 is 8. 2x1 plus x2 minus x3 is 1. So first off, let's check some things out. What's the coefficient matrix? And what size is it? So what do you think? And by the way, often the coefficient matrix is often denoted A, all right? So we'll let A equal our coefficient matrix, and we're just using the coefficients, right? And we're not looking at the constants at the column of constants. So do you see this is like a 1x1 minus 1x2 plus 1x3, etc. So we would have 1, negative 1, positive 1, and then negative 1, positive 3, and negative 2. And then positive 2, positive 1, and negative 1. So this is our coefficient matrix. Now we often call the, I should have had you find the constant matrix. So the constant matrix is often called B. So we'll learn about vectors soon, but it's denoted like this, and our constants were 2, 8, and 1. Cool, cool. So this one has a size of how many rows? Beautiful. 3. How many columns? Awesome. 1. And A, what is the size? Awesome. 3 by 3, because there's 3 rows and 3 columns. Now, when we said adjoin up there, you're basically adjoining this A and B. So if we look at some matrix B and we call it this adjoined matrix, so A is adjoined with this B matrix, this where B is the matrix of constants, that vector, right? So this B would be equal to our coefficient matrix, which is 1, negative 1, 1, negative 1, 3, negative 2, 2, 1, and negative 1. And the next column would be the matrix of constants, and that was 2, 8, 1. That was a column matrix. And so this is our B. And what is the size of B? The size is perfect. 3 rows by 4 columns. Okay? All right, so let's solve this system and see if it's consistent. All right? So let's check it out. Here we go. Now, we use the notation like I emphasized before. So what I mean is this. We have this matrix here, and it was 1, negative 1, 1, and 2, negative 1, 3, negative 2, 8, 2, 1, negative 1, and 1. And we're actually going to go through and solve this system. And this matrix we decided to name B, okay? Well, what we're going to do is we're going to do these row operations so that we get a matrix which is going to be equivalent. And that equivalent matrix will be in row echelon form. And then we'll be able to back substitute and solve the system. Are you ready? Okay, so here we go. Our first step, okay, remember we want to get this in that upside down triangle kind of format. So I want to get a 0 in these. So these entries here, I want to have be 0. Cool. So you got to do it a step at a time. Okay, so in order to do this, let us just add, right? So we've got our row 1, right? If we add row 1 and row 2, we want to have a new row 2. So row 1 plus row 2, and then that tells us that we get this new row 2. Right. Rewrite the matrix exactly as it was with the exception of the row that's going to change. And so what's really happening is you're kind of doing it in your head, meaning all of the computations we did before. So row 1 and row 2 are not changing before we add them. So if I add 1 plus -1, what do I get? Good, I get 0. So I added, the 1 and the -1 here. If we add -1 and 3, we get +2. Adding 1 and -2 gives us -1, and adding 2 and 8 gives us 10. So believe it or not, this is an equivalent system, an equivalent matrix, right? So now our next step is we got a 0 there where we wanted. We now need to 0 out the 2 that's in the third row, first column. Third row, first column. So here we go. I'm going to have to adjust one of the rows, right? One or more of the rows. So I think the easiest thing to do would be to say -2 times row 1 plus row 3, and we want a new row 3. Okay, so the changing row now is row 3. So I'm going to rewrite rows 1 and 2 exactly as they are in this previous matrix here. So 1, -1, 1 and 2, 0, 2, -1 and 10. And then the row that's going to change now is row 3. So remember, if you multiply row 1 by, I'm sorry, I did not put the 1 here. If you multiply row 1 by -2, what's going to happen? You're going to have -2, +2, -2, and -4. Those are the numbers you'll be working with, right? And then you'll be adding that to our existing row 3. And that's kind of where people get a little confused about matrices, because that step is done in your head typically. All right? You'll get used to it. Don't worry. All right, so here we go. I'm going to write the result of adding -2 row 1 plus row 3 in our new row 3. So -2 plus 2 is 0, which is what our evil plan was. +2 plus 1 is 3. -2 plus -1 is -3. And then -4 plus 1 gives us another -3. Cool? All right. So next up, we need to get rid of that 3 that's in the third row and the second column. Good so far? So here, what do you think we should do? So now we need to use row 2. We need to transform row 2 and row 3 in order to zero out the 3 that's in the third row and second column. You don't want to use row 1 because if you do that, you'll end up with a 1 in the first column of row 3, and then that would be frustrating. We'd be going in circles. So here we go. I'm just going to go ahead and say -3 row 2 plus 2 row 3. That'll set us up to zero out the 3 in the third row, second column. And this is going to be a new row 3. So now let's do it. So we would end up with -3 times 2 is -6. 2 times +3 is +6, right? So actually, let's go ahead and rewrite the rows that aren't changing. Okay, so now, -3 times 0 is still 0, and 2 times 0 is still 0. So this one here is still going to be 0. Not a lot going on here. Now here, -3 times row 2. So -3 times 2 is -6. +2 times row 3. 2 times 3 is +6. When you add -6 and 6, you get 0. -3 times -1 is +3. 2 times -3 is -6. So we'll end up with a -3 here. And then for the last part, we'll get -3 times 10 is -30 plus 2 times -3. 2 times -3 is -6. So we would get -36 when we add those. And now what do? We put it back into the system of equations, all right? So this here is equivalent to the system 1x1 minus 1x2 plus 1x3 is equal to 2. 0x1 plus 2x2 minus 1x3 equals 10. And then 0x1 plus 0x2 minus 3x3 equals -36. So do you see how easy that's going to be to solve, right? So this row here, do you see that x3 is going to equal to +12? And then what happens? You take your 2x2 minus your x3, right, which was 12, equal to 10, and that's going to give us that x2 will be 11. And now solving for x1. So x1 minus 11 plus 12 has to equal to 2. So we would get, let's see, -11 plus 12 is +1. So we would get x1 would be 2 minus 1, which is 1. Cool, cool? So let me show you where I plugged those things in. We ended up getting 11 for x2. And then x3, we had gotten 12, right? So that's where we plugged that into 2 of them. Groovy? And that was from here. All right, very good. So now we're going to take a look at how we would do this in Octave, which is really, really cool. So we're going to check our result using Octave, which ends up having the same commands as MATLAB, but it's free, all right? So here, what you want to do is you want to go to the very bottom of the page and you enter in the augmented matrix. And so in this particular one, I named the augmented matrix B. So you use brackets to designate a matrix, and you want to use a space between entries and a semicolon between rows. Okay, so I'm going to go ahead and enter in our matrix, all right? And remember, I had named it B. So I'm going to say B equals, you don't always have to put a space, but I kind of err on the side of being careful with it. So a bracket tells the computer that you're going to be plugging in a matrix. So we had 1 space, -1 space, 1 space, 2. That's the first row of our matrix, our augmented matrix. Then we do our semicolon. Our next row was -1, 3, -2, and 8. And then our third row was 2, 1, -1, and 1. Cool. So you need to end your matrix notation, so put a bracket. And then when I hit enter, this is what it looks like. Cool. So this is a different command line than I pasted in our guided notes, but that is that's fine. They don't really matter, the command lines, to us anyway. Good so far? Now, the good thing about naming your matrix is it's in there. So like if I do B right here and hit enter, look, it comes right back. So no matter what you do with your matrix B, you can go back to it. Now, Octave, okay, I don't think has an ref command, but we'll see. Ref B. See, it doesn't do REFB. And the reason it doesn't do it is because there's an even groovier form that is called reduced row echelon form. And you'll see that your calculator has that as well. And so that one is RREF, surprise, surprise. And we want to do RREF on B. And look what happens. Isn't that awesome? I like it. How do we interpret this? I mean, do you see that our coefficient matrix is what kind of matrix? Awesome. It's a diagonal matrix, right? It doesn't always turn out diagonal, because if you end up getting a dependent result, then what happens is you'd have numbers in the top triangular part, all right? But that lower triangle is going to have the zeros that you want. But notice there's no coefficients, so you don't have to go back and plug stuff in. So here, if you ever get confused, all you do is put it back in the form of a system of equations. So what did we get? We got 1 times x1 plus 0x2 plus 0x3 equals 1. 0x1 plus 1x2 plus 0x3 is 11. And 0x1 plus 0x2 plus 1x3 is 12. Well, this system is equivalent to x1 is 1, x2 is 11, and x3 is 12. Well, that one's not very hard to solve, right? So our answer for this problem on the computer would be it intersects in one ordered triple. And so the ordered triple is 1, 11, 12. And this is a consistent system. With beautiful independent equations, because we did not get infinitely many results, right? And we are done. Cool. I hope you have a wonderful morning, afternoon, or evening whenever you're watching the show. And if you like what I'm doing, please subscribe. I'm looking to get 1,000 subscribers. So it'd be very cool if you would subscribe and tell all your friends. Bye.